In this lecture, we are going to look at an alternative and better way of building a logistic regression model in PyTorch. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. The motivation behind doing this is that when we perform the sigmoid, we have to do an exponential operation. The problem with that is that exponentials are numerically unstable due to the fact that they grow very fast with respect to the input. In addition, the log term in the binary cross entropy is also unstable for similar reasons. Well, it turns out that because the binary cross entropy loss has a log in it, it almost cancels out the exponential in some sense. Although we won't go through any derivations in this course, the end result is that if you know you have to do both the sigmoid and then the binary cross entropy loss right after, there is a way to combine them into a single function so that you avoid numerical instability. In particular, you can express the loss only in terms of the activation, which is also called the logit in this case. If you've ever studied statistics, then you may have heard of this term before. Otherwise, don't worry. Basically, the logit is just the input into the logistic function, and the logistic function is just another way of saying the sigmoid function. So in this script, pretty much everything is exactly the same, except in two places. The first place is when we create the model. So before, we used the sequential and combined the linear layer with a sigmoid layer. But in this script, we no longer need the sigmoid since that's included in the cost calculation, and therefore our model goes back to being just a linear model. The output of this model is the logit. Then, when we create the loss function, we use BCE with Logits loss instead of BCE loss like we were earlier. As its name suggests, this function calculates the binary cross entropy loss directly from the logits. As you can see, everything after this is the same as well. So our training loop is the same and we get the same results. One more difference we have to pay attention to is when we make predictions. If you recall, the sigmoid always outputs a number between 0 and 1, and we interpret that as a probability. So when we want to make a prediction, we simply round those probabilities. Anything greater than 0.5 is a prediction of 1, and anything less than 0.5 is a prediction of 0. But what do our predictions look like now, since the output can again be any number? In this case, we just go back to our geometrical picture. You can also think of what the sigmoid actually does, and if you follow that logic, this should make sense. If you recall, anything on one side of the hyperplane, defined by our model, is positive, and anything on the other side is negative. The sigmoid simply maps all the positive numbers to probabilities greater than 0.5, and similarly, it maps all the negative numbers to probabilities less than 0.5. Thus, it's very easy to make predictions. We simply check if the model output is greater than 0 or less than 0. Anything greater than 0 is considered a 1 prediction, and anything less than 0 is a 0 prediction. Note that we can use the greater than sign directly, even though the greater than sign returns trues and falses. As we discussed earlier, in Python, true is 1 and false is 0. Therefore, we don't need to do any further processing. Once we have our predictions, we can check the model accuracy, and again we can verify that the result is the same.